Yeah, good morning to one and all. Myself, Dr. Paul Raju. Today I am here to teach the course Structural Analysis. This course code is 22CE 2201. So this is we are offering for the semester, event semester, academic year 23-24. Now I would like to talk about few important things related to this course. Don't try to cheat. If caught, consequences will be severe. Maintain silence in the class. If you need to discuss something more important than the class, please go outside and discuss. And in the CO1 syllabus point of view, I would like to talk about first moment area theorems. We have two theorems actually. The first theorem is the change in slope between any 2 points on the elastic curve equals the area of the M by E diagram between the 2 points. That means to find out the slope and deflection, we have a very good methodology approach using a moment area method. The method itself, it is saying moment area method. So moment area method theorem means once you calculate the Bennett diagram, you have to divide it by M by EI diagram. So EI multiplication. Once that EI multiplication happens, then the M by I diagram will be ready. Then the second moment area theorem is based on the relative derivation of tangents to the elastic curve. So with that one, you can see the one beam when you cut at the center, how the free body diagram and reactions are taken into consideration. Then you can see here this is the better understanding about the diagram, how to take the moment area theorems. Then it is important to realize that the moment area theorems can only be used to determine the angles and deviations between two tangents on the beam's elastic curve. In general, they do not give a direct solution for the slope or displacement at a point. So now you can determine the slope at points B and C of the beam shown in figure A, and then there is a E and I is being given. Now you can see the one example, this diagram, how to place the values and how to calculate the movement diagrams. Then the area of the M by A diagram is nothing but a slope, whereas area into centroidal distance is nothing but a your displacement actually. So there is a solution. You can see we have one cantilever beam with end point load 10 kilonewtons B is being applied, and there is a B, C, and this span of the beam is 10 meters and the center of the point is 5 meters. And for suppose if I wanted to calculate the slope and deflection at point B, then how to proceed, you can see here. So this one is showing that then once you calculate the bending moment diagram, obviously for cantilever beam, the bending moment diagram magnitude of bending moment will be at the fixed end, whereas at the free end you will be having zero bending moment. So like that, when you calculate bending moments, then you have to do intentionally M by bending moment value divided by A, then the area of that particular zone. But here what it is happened, it is looking like a trapezoidal actually. So for that, it is being divided into one triangle and another one is in rectangle shape. Then easily I can put the area of the rectangle and area of the triangle actually. So like that is the way you have to calculate the slope of the that particular beam using this moment area method. Once you get the slope and slope into central distance, you will get the displacement. Then one more example is being given here, that determine the deflection at points B and C of the beam shown in figure. Values for the moment of moment of inertia of each segment are indicated in figure, and take E equals to 200 GPa and there is a numerical is being given like this. But in this numerical you can easily observe that the beam is not maintaining uniform cross section throughout. It's not a prismatic, it's a non-prismatic actually, and that too at the free end there is a one anti-clockwise movement is also being applied, that is 500 Newton meter, and you have different moment of inertia also, that is IAB equals to 8 into 10 to the power of 5 mm to the power of 4, IBC equals to 4 into 10 to the power of 6 into mm4, and that is up to A to B you have 4 meters, whereas from B to C you have 3 meters. Then as usual, by doing our regular calculations, by applying the equation of equilibrium, summation of fx equals to 0, summation of fy equals to 0, summation of moment at any point equals to 0, since the cantilever beam is a statically determinate structure. So to analyze the determinate structure we required only 3 equations, because there are unknowns are also are going to be 3. So when unknowns and equations are same, when you get that difference value is 0, then that beam we used to call it as a statically determinate structure. So in that way, in regular process you can calculate the magnitude of the bending moment. Once you get the magnitude of the bending moment, then you divide it by EI, that is flagell rigidity. Then whatever you get that value and the diagram, that diagram area of the particular portion, then you will be getting slope of that particular point actually. For suppose if I want to get the slope at B, if you want to get a slope at C, then you have to add the AB diagram as well as BC diagram. For suppose particularly you want only up to B, then you have to add only or calculate the area of AB diagram only. But if you want at C, then you have to add it both AB and BC, because it's a consolidated one or overall one. Likewise, you are going to get the slope at the particular or required appropriate points, and similar to the previous problem, once you get the slopes, then getting deflections is very simple if you know the centroidal distances for the particular shapes. Here the main knowledge is required, that area of that particular shape and centroid of that particular shape. For suppose area of the square, you know that B into B, area of the rectangle L into B, area of the triangle half into B into H, area of the square pi d square by 4, area of the not square circle, so area of the trapezium A plus B by 2 into H, that is area of trapezium. Likewise, when you have another kind of shapes also, you must know the area formulas as well as centroidal formulas also you must know. For square generally it's a B by 2, and for rectangle when you are coming along the lengthwise L by 2, and when you are coming along the breadthwise it's a B by 2. And then triangle also, you know that one side wherever the small portion is there you will get 2/3 B, and then another one 1/3 B. Likewise when you are coming from top also, that is 2/3 H and 1/3 H. So that formulas you must know, so that to calculate the deflection formula and deflection magnitude will be very easier by using this moment area method. See, this moment area method is a direct method, and it will give the direct values, and the procedure is going to be very easier to get the that required values of the slope and deflections at the required points. And there is a one more numerical. By inspection, the moment diagram for the beam is a rectangle, we will construct the M by A diagram relative to IBC. IBC is nothing but a that is moment of inertia. IAB equals to 2 IBC. Then numerical data for EIBC will be substituted as last step. The coupled moment at C causes the beam to deflect as shown in so. The tangents at A, B, C are indicated. We are required to find delta B and delta C, and these displacements can be related directly to the deviations between the tangents, so that from the construction delta B equals to deviation of tan B relative to tan A, and minus delta B equals to TBA, and delta C equals to TC by A applying theorem to moment of the area under the M by EIBC diagram between A and B computed about B. Then deflection of beams using conjugate beam method, that is another very good method. But before I go to that method, I would like to summarize the method of moment area method. Using this moment area method, the numericals are not only limited to cantilever examples, even you can apply that for simply supported beams also. But applying moment area method for statically indeterminate structure is quite difficult. This method is the best suit for statically determinate structures. That too, I would say, like cantilever with end point load, cantilever with UDL, simply supported with center point load, and simply supported with overall UDL. Likewise, even you can make propped cantilever with the internal hinge also, it will be a statically determinate structure. For this kind of structure also you can apply this method, but you must know the typical analysis of the one particular given beam using regular process. That means by applying the equation of equilibriums, you have to draw the both shear force and bending moment diagrams. But in this method you don't require any shear force diagram, but you require bending moment diagram. Once you get the bending moment diagram, you convert that is into M by A diagram. But M by A diagram, why you do want to convert? Especially when you have a different moment of inertia, that time automatically diagram will get changed. Diagram will not be remain same actually. But when you have a moment of inertia throughout same, the diagram remains same. Then except the value will be changing. That means M by EI diagram you will get. Once M by EI diagram comes, only this method you can able to apply thoroughly as per the methodology of moment area method. So that is M by EI, area of M by EI diagram is nothing but a slope, and the slope if you want at the particular points limited to up to there only. For suppose if you want deflections at that particular point, area of the M by diagram into central distance is going to be your deflection magnitude actually. So that is all about your moment area method. So with that note, I can switch over to the another method, that is deflection and conjugate beam method, that I am going to shifting into the session 2, lecture 2.